to today's webinar. My name is Guido Wolf. I'm the organizer of the webinar, and it's the third part of our webinar series about the essential principles of power. Before we'll start the presentation, I'll give a short explanation about the webinar. During the presentation, you can ask questions using the control panel and just type in the questions and we will answer them at the end of the presentation. We will also record the presentation and a link to that recording will be sent to you automatically tomorrow. And if you have any further questions or would like to ask Ken something or me afterwards, just drop us an email and we'll get back to you. So before I hand over to Ken, just a few words about our company. So Lecroy was founded in 1964 by Walter Lecroy and is based in Chestnut Ridge, New York. Originally, we come from the high-speed digitizer world in the particle physics research. Today, we are mostly famous for our technology on oscilloscopes, and we have the widest line of real-time oscilloscope ranging from 40 megahertz to 100 gigahertz. Besides that, we are also market leader in the protocol analysis and have a long history of innovations. In 2012, we were acquired by Teledyne Technologies, and since then have our new name, Teledyne Lecroy. So today's presenter is Ken Johnson. Some of you may have heard him already in previous webinars. He's since over 15 years with our company. He's product manager and director of marketing and product architect, a real expert in the field that he's presenting today. He has some degrees and also some patents and is very experienced with power electronics. So I'll hand over to Ken now and enjoy the webinar.
Thank you, Guido, for the introduction. So this is part 3, and if you watch part 1 and 2, what we'll be spending time on in part 3 is some very specific use examples, and so I think you'll find this very interesting. So first of all, what we're going to do is just review our agenda. So we're going to define what we mean by power and do a very brief overview, and then get right into the solution compares and the case studies. And then we'll take Q&A at the end. Okay. I always want to define power. Power means a variety of things. I always say it's like a blind man describing an elephant or a series of blind men. So depending on what you're talking about, power can be very different things. And so in the next three slides, we'll just talk about the power focus of this presentation. These are just a few of the power definitions. So basically, many people know power is what they get out of the wall plug at their home. So utility grid, line power. There's, on the opposite end of the spectrum, power semiconductor device power, the power consumed by a MOSFET or an IGBT during its operation. There's digital power management, like what you'd find on a circuit board or a motherboard, where you have to manage all the different DC power rails and how they start up in sequence and whether they have good power integrity or not. Then when you start putting all these things together, devices and boards together, you get some sort of power electronics product, and that has AC input, typically 50, 60 hertz input, and output of pulse width modulated signals of some kind. So that's what we call a power electronics inverter or a converter. So you might be involved in power testing of that. And then when people may mention power, a lot of times they're talking about power analysis as done by a specific dedicated power analyzer instrument to measure watts or volt amperes or something like that. So this is AC grid power. We all know it's a sinusoid. It's 50 or 60 hertz depending on where you live. And a power conversion system like this, cascaded H-bridge, just takes that AC input in, it rectifies it, creates a DC bus that's stiff and has storage. And then from that, it uses that DC signal and chops it up using pulse width modulation. And then it recreates something that looks like a PWM waveform. And the more comprehensive systems will have both a positive and negative going excursion, which closely resembles that of a sine wave. So that's the focus of our discussion today, is this particular type of system. Okay, a quick power overview. As many of you know, we generate electricity, we transmit and distribute it to the location where it's used, and then we consume it. So the generation historically was centralized by the utility. Now it's becoming much more distributed on a rooftop or in a wind farm or something like that. The transmission is through cables and transformers to step voltages up and down and deliver the current. And finally, we consume it directly from the line or increasingly through some sort of power conversion system that looks like one of these things. Historically, you could say this is what the flow of a power transmission system looked like. You generate, you'd step up from 25 kV or so and transmit at very high voltages. Customers would start picking it off at 69 kV, let's say, or around there. You'd step it down. Other customers, commercial locations, would get it at medium voltages, and you'd step it down further, and you'd use it at the household level at 120 or 240 volts. So centralized, one-way power flow, overall power delivery efficiency of only 32%, of which the actual transmission part itself accounts for a fairly substantial portion of the losses. So 7% losses overall, just in the transmission and distribution of that electricity. So it's really very, very grossly inefficient. Since it's so grossly inefficient, there has always been a focus on optimizing it. So if you were a manufacturer of power transformers that you sold to a power utility, they would want to know what the losses were. They'd want to know what the core losses were and the load losses due to the copper, and they want to know the efficiencies. And they would buy a certain efficiency, and they want to make sure they're getting it. So it would be tested at a factory prior to shipment with something like a power analyzer. It's a 50 or 60 hertz test. They'll measure the core loss or no load loss. They'll measure the load loss. They'll calculate the efficiencies, and they provide a report to the utility customer as part of the sale. Likewise with motors. Nearly half of worldwide delivered electricity is consumed by motors. Large motors make up 90% of that consumption. So if we look at the unit volume, it really follows the 10-90 rule. 10% of the motors, medium and very large, are only 10% of unit number, but use almost 90% of the electricity. And then the unit volume is 90%, but they only use roughly 10% of the electricity. So again, and most of these were line powered right off the line up until the, let's say, the 1990s. So historically, companies that made electric motors would report on their efficiency. They would have a dynamometer stand to provide a load. They'd run the load in many different, what I'd call static test configurations, a certain torque or a speed and load percentage on the motor, and they would create a report. And so they would use a power analyzer to do that. And the power analyzer would essentially return numbers and calculate. It's really a validation tool. It was originally designed for a test stand like this, which is one of the reasons why they have a very limited amount or limited capability for measuring analog torque or speed, which is mechanical power. So it's not really an integrated design tool. It's a validation tool. But what it does extremely well. Now, today's power grid is evolving very rapidly. It's causing a lot of disruption you've probably heard about. But the power flow used to all be one way, but now the power flow near the customer is becoming two-way, and distribution is becoming, or generation is becoming very distributed. So you have things like a car that might pull power from a battery and give that back to the grid, or some sort of combined heat and power, or a solar PV system, or a wind farm. And they're all taking power to and from the grid in very unpredictable ways, and the power flows are becoming very complex. As that is changing, what that means is power electronics are going to migrate from your switch mode power supply in your laptop PC, migrating into solar PV inverters, which is happening right now, and it drives, and now it's going to be migrating into the products that utilities buy. So it's a very exciting time in power electronics. You know, basically in the last 20 or more years, the design complexity and the power levels have gone from very low to very high. So more than 1,000 watts and three-phase complexity. Switch mode power supplies, very popular in the late 80s. Then it moved to smaller drives, then to larger drives and solar PV inverters, now very exotic drives in very demanding applications like automotive. So we're going to pause for a moment, and I'd like to ask you to answer a polling question. and you can choose one or more answers here. And basically the question is, what products are you designing and testing? So we talked about 50, 60 hertz core coil devices like a transformer or a motor that's not running on a drive. We talked about switch mode power supplies for a laptop computer. Those are single phase power electronics devices. We talked about a cascaded H-bridge, something that would be used in a three-phase motor drive or a grid-tied solar PV inverter. That would be a three-phase. Perhaps you're involved in the design of the embedded control systems, which would be the system that runs any of the above things here. Or maybe you're a systems engineer that's involved in putting together the full package of systems and making sure it meets the performance needs. Or maybe you're just curious, you don't do any of this, and you're just here to learn a little bit more about the field. And looks like the poll is going to be open here for just a few more seconds while you make your choices, and we will wait for that to conclude. Okay, so we've closed the poll. We'll continue again. And now what we're going to do is we're going to spend time talking about the solution comparison, the kinds of products people use in this field. So there's power analyzers, there's oscilloscopes, and there's a product we call a motor drive analyzer, which combines the best attributes of both these things. So if we look at what the field looks like in terms of what a solution choice is, and I've drawn a triangle here, and at the apex of each triangle is some characteristic that's needed. So for instance, at this apex, three-phase power analysis is often needed. For that, you need a sufficient number of channels and a good enough resolution to accurately measure the power quantities. Then motor integration, the ability to get a torque or a speed signal in so you can calculate mechanical power off the shaft is very important for some people. And then oscilloscope capabilities for debug of the control system or other higher speed events. So you typically need high bandwidth, very high sample rate, good long memory, digital logic, MSO capability. You've got serial triggers and decodes you need to look at your serial streams on your embedded control systems. And you're probably thinking about doing some device testing as well with something like this. So each one of these things, the oscilloscopes, they do the oscilloscope things really well. A power analyzer, the better ones, combine the three-phase power and the motor integration. So these Yokogawa products are very common. We make an 8-channel 12-bit scope, so that sort of does two of these things here. It doesn't by itself calculate power, but we calculate power in our motor drive analyzer. So the motor drive analyzer combines really the best attributes of all these things. A traditional power analyzer is a static measurement device. General purpose scopes for power testing and three-phase especially don't have enough channels. They definitely 8-bit resolution is not enough. And this product really combines it all. It's got 8 channels, 12 bits, plus the power analysis capability. And by putting that all together, we get this dynamic, very unique dynamic transient power analysis capability. If we look at how that compares, this is just to compare. Typically, people tell me, hey, I have a 4-channel scope already, and I have a power analyzer. What's really different about what you do? And the difference is that by putting all this together, we can get the dynamic power analysis capability. And we also provide better complete test capability by having so many more channels. And we'll talk about that in a little bit. And it's a complete solution, so I'm going to introduce this block diagram here as something that we can use to describe how every product might fit into this space. But we can test anything in the control system here, from serial data to analog to digital. We can integrate the motor in a very complete way, and we can measure the power quantities and not just calculate numbers, but we can also display the waveform, which is extremely helpful. Okay, what does a power analyzer do? Power analyzer tool does one thing really, really well, and that is it provides numbers of what the power quantities are. So that's what I'm showing by this calculator here. But they have very limited waveform capture. When they offer it, the records are usually very short, and the sample rate and bandwidth is very low. So it's good enough for power calculations, but it's not good enough for a lot of debug that you might want to do within these signals or debug anywhere else in the circuit. And you certainly can't debug anything in the control system. If we can compare a power analyzer to our solution, basically a power analyzer has short record capture. Sometimes they show the waveforms, but no dynamic power analysis and no complete test capability. 4-channel scope, it's what everybody has, 4-channel 8-bit scope. A limited capability, not surprisingly, we know that well as something that debugs control systems, and it can get into maybe one leg of a 3-phase inverter and look at activity on gate drives or something and correlate that to the control system. It can also measure device power as well, but generally speaking, it has too few channels for most people in this application. 4-channel 8-bit scope, it doesn't do any of the power calculations, and it doesn't have complete test capability. So if you have both these things, as we talked about, that's better than having only one, but they operate as different systems, and it's extremely difficult to correlate the power interactions, and so basically it doesn't function as really one unified instrument. If we look at the complete solution summary here, and what we're going to show in some of the application examples is this here. There's a lot of different things you can do when you put all the capabilities in one product. So this power analyzer here, it does a great job of measuring 3-phase electrical power. It is the best at that. It usually really provides just numbers. Yes, there's some waveform capability, but it's very limited. The better ones do a pretty good job of integrating mechanical power, but the sensor inputs are usually those found on a validation stand, and they're not the Hall sensors or quadrature encoders or resolvers that most engineers are used to working with. And they can't do any of the scope type activities. You can't dig into the inverter subsection with your power analyzer and look at the voltage across the capacitor or something like that. So it's very limited, no embedded debug, and of course these products here as well. Very limited. A scope is reasonably good at the control systems, not so good at control power interactions, and the motor drive analyzer really ties it together the best. One thing I mentioned is we have the ability, and I'll show this in some of the slides, we can integrate as a speed sensor a quadrature encoder or a resolver or a Hall sensor, and that's typically not possible with a power analyzer. Okay, so one thing a power analyzer has that's very different, and this does provide some benefit in accuracy and usability, but also a penalty in terms of flexibility. So a power analyzer has elements, input elements for voltage and current, or for other things like sensors for torque and speed. And these are typically high voltage isolated from each other and from ground, which is great. You like that. The problem is that they're built in, the fact that they do this one thing for power measurements for the voltage and current signals, they don't have any flexibility for non-power signals. So they're great for measuring power, voltage, and current signals and then using that to calculate power. But the problem is that I can't flexibly use it for something else. Our solution here, we need probes. They do add some cost. They do reduce accuracy a little bit, but they provide a lot more flexibility. If you're looking for premium gold standard accuracy, the power analyzer is better at that because they have input elements. If you're looking for pre-compliance accuracy on the power side, then the motor drive analyzer is more than sufficient for that. And it gives you more flexibility. Okay, we'll pause for our second polling question. I'd like you to answer, what type of equipment do you currently use today for design, validation, and testing? So we've talked about almost all these kinds of solutions, a power analyzer, an oscilloscope of any kind, a data acquisition system, which would be something kind of in between these two things, perhaps something that has very low bandwidth but long capture time, maybe more than 4 channels on a scope, very low sample rate. And then maybe you use a power analyzer and a scope, or a power analyzer, a scope, and or some data acquisition system. So if you answer one of these questions for us, tell us what you're using, and then we'll proceed. So we're going to pause about 30 seconds or so for that. Okay, so the poll's closed. We're now going to proceed. Let's go to case studies, which is probably why a lot of you are here. These are really very interesting. Let's first take a look at a 480 volt 3-phase 1.5 horsepower AC induction motor drive. And we're measuring an input-output efficiency and performance for a short period of time under no load conditions. So this is what it looks like. So basically, there's a lot of information here. I'll explain it. These are my two AC input waveforms. I'm using a 2 wattmeter method for my power calculation, so I need 2 line-to-line voltages on my input and 2 line currents on the input. And then on the right side here, these are my drive output waveforms. And I've got this set up in a tabbed mode, so you can see there's a label that says AC input and drive output on the right side. I'm taking a very short record. It's a ½ a second total, or 50 milliseconds per division. I'm calculating mean power values here. This is very equivalent to what you get on a power analyzer. This is a summary of my setup that describes the 2 wattmeter method in both cases and the channels I'm using and how I'm making the sync calculations. This is just the same display, but a larger view of it with the menu closed. And then what I've done here is, what I've got is this again is my AC input acquired waveforms. I put cursors on here just so you can correlate this time location with this time location. On the right side here, I've got the efficiency tab open. And so I'm plotting efficiency. This is per cycle efficiency over time. And I'll explain that in a slide or two in more detail. These basically all are waveforms that I calculate with the MDA product. You see I still have the numeric results down here where it shows me I have about a 34% efficiency. These signals here are my sync signals that I used for the calculation of the power quantities in this table here. And you can see if you counted these periods or just look at them, the drive output signal is a longer period or a lower frequency than the AC input. So we're using 2 different syncs for that reason. This is a close-up view of just the information on that tab. This is efficiency over time. So vertical is efficiency, and you see a lot of different, but it looks like a stair step. That's because each one of these locations here is one overlapping period. So if this period or this period changes, we make a new efficiency calculation. We're actually going to present this method at APEC in a few weeks. So if you're going to be there, please look us up and stop by. So I've got 28 AC input periods, 22 drive output periods, and therefore we're making 50 efficiency calculations overall. This shows the mean value for efficiency here. This shows the full range, 50. It shows my minimum and my maximum, and then the mean value, which is carried over to here. Okay, so that's a static test. Now, that's very similar to what you might use a power analyzer for. This is now the same test we did before, but this time we're running it under a load condition. So what you're going to see is now the current increased here on my drive output, and I've changed the scaling. Otherwise, I've used the same time period. But note that under load, my efficiency went up from about 34% to 73%, and my power factor increased as well. I'm looking at a full spectrum output on all these calculations, so the power factor is a little lower with those distorted waveforms than what you might see if they were pure sine waves. Again, this is the same view as we saw before, but now it's under load, so it should look the same. Just a close-up here, 73% efficiency, and that carries from this mean calculation in this total of 50 waveforms right here. Otherwise, the same basic test I did before, just under load. Okay, now let's combine these two things. Let's say we're going to go from a no load to a load situation, and we're going to monitor that dynamically. This might be what you find during a startup event, for instance. And we can use the long acquisition memory of our capture system to do that. So here is now the combination of a low load event in the beginning, let's say, and then we turn the device on. You can kind of see that happening right here as the drive goes on. To explain again, these waveforms here, this is the AC input on the left side. That's a 10-second capture, or 1 second per division. This is the drive output waveforms right here on my right side. And then immediately to the right of those are the zooms of the corresponding waveforms to the left. So this section here is zoomed right here. And so you can see that's the AC input that we kind of know from the previous example. This is my drive output at startup. There's no voltage at the output, and then we ask the drive to start and start turning the motor, and so you see this startup event right here, and that's the zoom of that. Now I can change the zoom ratio, which I've done here, so we're starting to see more of these cycles, and this is a 5-time zoom ratio, so I'm looking at 1/5 of the full acquisition, or about 2 seconds total. I have a 10-second acquisition. This is 2 seconds of that full acquisition during the initial startup period where the shaft starts turning. If I go all the way to the end, I can just change my zoom position and ratio, and I can get to the end, and this is what it looks like under a rapidly ramping speed situation with some load on it. And so I can scan through the waveform and look at that. Now what we can also do is we can use a capability called Zoom+Gate, which we've enabled here from the front panel or from the software UI. And we can turn our numerics table on and show what the power values are for the ABC or the input and the RST or the drive output. And so we calculate all these things. It's a rather simple setup. And you can see a power value here on the input of almost 59 watts and on the output of 29.5 watts. Those are the mean values for this full acquisition. And these values are now just gated. They're just gated to the zoom only. So this area right here, as I change that zoom ratio, these values will change in real time. This is the same image that you just saw, but now it's a full screen with the menu closed. Okay, so basically once I choose to look at this particular location of my full acquisition right here, once I choose to look at that place, I can just simply click in this table here, and when I click in that, a waveform's created. And the waveform is basically a per cycle waveform versus a value versus time. It could be any value that we can calculate. So it can be efficiency or voltage or current or power for the sum of the 3 phases, for an individual phase or whatever. So I've just, all these special highlighted things right here are also waveforms over here now. And they have a description in this box that matches the color code. So this is the efficiency of the drive output right here. And I can see how my efficiency is changing over time. I can look at my power on my startup. On the drive input, it increases and peaks rapidly and then comes down. And I can look at the power on my drive output, also goes up. As the motor gets up to speed, it goes down, and then as the load starts being applied, it's going up again. These things here are plots of the RMS voltage and current versus time, and they're labeled right here. So I can look at the those values as well. So this is a detail of just those per cycle calculated waveforms, and these can have cursors put on them, and I can read a value. So this is the efficiency right here. If I put a cursor there and there, I can get a value. Well, we didn't really have. It was the startup event. There was no efficiency calc because it was the very first cycle. But by here, we can see our efficiency is peaking at 46%. And so I can run these cursors through and get a value at any time. And as I change the zoom ratio, these waveforms will change and display updated information here on just the zoomed area. Now, there's a lot of information here. So we've made it pretty simple. You can use a UHD 4K extended desktop monitor with this instrument, so to see all the stuff very, very large. And we have this tab display mode to let you label them and show pretty much any combination of things you like. So the summary here for our solution is for the static power analysis. We can do that. The power analyzers, of course, can do that. That's what they do really, really well. We can also do this dynamic analysis with Zoom+Gate and statistics and the per cycle waveforms and very long captures, and that's not possible with a conventional power analyzer. We can calculate efficiency. This is, the power analyzer for sure, is the gold standard for accuracy. If you are a validation engineer and you need to calculate efficiency to like 0.2% and provide a report, you have to have a power analyzer. There's no way around it. But if you're an R&D engineer and you want to look at efficiency to within about 1 or 1.5% perhaps, get a pre-compliance check, pre-compliance accuracy, especially in dynamic conditions, then we're a great solution for that. As you saw, you have to have a sync signal to make your calculations, and we do provide an overlay. So it shows you exactly where we're making the calculations, what the cycles are, which is pretty helpful. Okay, let's look at a brushless DC motor. When I say brushless DC motor, I mean something that uses Hall effect sensors and a 6-step commutation. And this particular motor is battery powered. It's a power drill I bought at a home center and took apart. And it's very interesting to look at this. So here we looked at the DC bus. So these are my DC bus signals here. And this is a 2-second acquisition, or 200 milliseconds per division. So these are my bus voltage and my bus current, and then these are the zooms, just like I showed before. I'm also vertically zooming here, so I can see this detail, which is kind of nice. These are my drive output waveforms. Again, I'm using a 2 wattmeter method. These are the full 2-second capture, and then the zoom right here. These are my analog torque and speed signals. I have this drill connected to a dynamometer here with analog torque and speed signals, so I measured those. But I also have a brushless DC Hall sensor on the 6-step commutated drive. And so I'm picking those off too with our MSO system and showing that as a digital logic system. Then what we can do is we can calculate all the numerics for power for both the DC bus, the RST drive output, and also the mechanical shaft output. And we can look at these different parameters here. These are mean values. And since we're using Zoom+Gate, these values here, for the moment, are only calculated on the zoomed area here, which is shown to the right of all the other displays. These here are the per-cycle waveforms, showing how speed, torque, and mechanical power is changing over time. Speed is shown orange, torque is shown with this salmon color, and power is blue. And you can see it's a 6-step commutated drive. You do expect there's some torque ripple. You can clearly see it right here. This cursor I put here, just so you can see, you can get a readout right there of speed instantaneously, but that also helps me to correlate it back to my original acquisition as well. So I can see right here, I'm kind of peaking at the stress on the DC bus. I can see what might be happening over here at that time. And by the way, this speed calculation here is made from the Hall sensor signals. A quick summary of this, it's pretty much like what we discussed before. We can do static plus dynamic. This product can't do the dynamic. The scope can't do any of those things. We do the full mechanical analysis. We can integrate the brushless DC Hall sensor, and these products typically do not. Okay, so where it gets very interesting is where you have a complex drive and control system, and you're trying to understand how the drive and the control interact with each other. This is where all the problems start, and especially the reason we stress dynamic capability so much is because that's where all your problems happen. Things rarely happen in steady state mode. The old example we all know is when you turn the incandescent light bulb on. Let's see, if you're over 40, you turn the incandescent light bulb on. It always fails during the power surge when you turn it on. It never fails when it's burning steadily, or rarely does. So it's the stress of the dynamic event that leads to failures. Those are the things we really want to look at, and we want to know how our control system is responding to the stress, of the dynamic stress of the system. So this particular example is a customer product that they shared their results with me. The product is a very small handheld tool that undergoes a very high-speed operation. The operation of the tool involves a reversal of a direction once per second. There's a lot of heat lost in the motor during the operation and the reversal. This is not what they want because it's a small tool that's held in a hand. Heat causes discomfort. It also leads to reliability problems. So things they wanted to test were trying to understand, is the control system affecting the reversal as it should? Is the drive output performing acceptably well under these circumstances? And what is the power or heat lost during the operation? Okay, so step one was to verify the control interaction. Basically, they wanted to look at their command signals, which are shown here on channels 1 and 2. This is yellow and magenta, and this is zoomed over here on the right. So you can see this dimmer area is the non-zoomed area, and then this brighter area is what's shown in the zoom. I've also, or this customer has also vertically zoomed so they could see this edge a little bigger because they really only used a very small portion of the display here. These are my inquired waveforms. In this case, this channel 3 is the encoder position of the rotor. It's just a voltage feedback signal that they use in their control system. And 0 to 360 degrees is one ramp of their, one complete revolution of the motor shaft. Then they sense actual speed of the motor and a commanded speed of the motor. This channel here is sensed actual, and this is commanded from their control system. And then everything here is zoomed. So basically, when these signals go high, the motor reversal should begin. And when this signal goes low, the motor reversal should have completed before that time. And so they're trying to correlate that. So that can be seen very closely here. The motor reversal initiates right here, and it's completed right here, essentially. And that's well before this amount of time. If I wanted, I could put cursors on that and measure that time. And they can see that the commanded speed closely tracks the actual speed. Now, step 2, to verify the drive output behavior. Again, this is showing a 2 wattmeter mode. So there's 2 acquired line-to-line voltage waveforms and 2 acquired line current waveforms. This is a 5-second acquisition at 50 megasamples of data, and it's 10 megasamples per second. So 5 seconds of acquisition, very, very long time. You get what we call a cheese block of data. So we're really going to have to zoom in on this at some point. But notice right here, you can see the motor reversal and then the motor operation. Motor reversal, motor operation, and so on. So you can see that there's a high amount of current being drawn. It takes a little time to settle down, and then there's some steady state operation before it reverses again. Okay, so the point here is to measure the power values during some specific areas of time. Now this is the full 5-second acquisition here. And so there's nearly 1,000 calculations that are made. I know that because I can look in my statistics here. It says 978. And so basically, this value here is a mean power value, the average power value for this full 5-second acquisition. But there's a lot happening in that 5 seconds of time. So a mean value like I get out of a power analyzer isn't really going to do much for me. But if I click on these boxes, these mean values here for RMS voltage, RMS current, and power, if I just click on that, then it creates this waveform here, and it highlights the box, and then it shows me, okay, the orange waveform in this case is power, and you can see this is power vertically and over time. And this is time correlated to this waveform right here. So this is a display of how my power is changing over time. Here's the steady state, right? Here is just after the reversal. Here is during the reversal, and then here is just before the reversal. So you can see there's a lot of change in the power. I'll also point out this cycle looks a lot different than this cycle. So just hold that thought for a minute. This is the current here. It closely tracks the shape of the power. This is the voltage here, which looks a little bit different than the profile. But in general, you can kind of imagine this times this is giving me that right here. But this is a calculated quantity of the RMS voltage on one cycle. This is a calculated quantity of the RMS current on one cycle. Then we take these 1,000 cycles or so and plot them over time, as we described earlier. So these signals are not probed. They are calculated and displayed as if you could probe them, which is a pretty cool capability. Right now what we want to do is zoom and gate, and we're going to zoom into one power cycle from the reversal initiation to the end of the reversal. And so now we haven't changed our setup at all. We've just created zooms using zoom and gate, and now we're looking at these areas here. This is one full motor operating cycle. This here are those same waveforms I showed you before, one full motor operating cycle. If you look closely, you start to see that stair-step type effect, so you can see their per cycle calculations. I've got cursors on here, and the reason I do is I want to get a time value. So I've got my cursor here and here, and the zoom helps me know exactly where to put them. And the delta time between the two cursors is just under a second. It's 907.7 milliseconds. So if I have the power value, which again, these power values in this table are now gated just to the zoom area. If I have that power calculation, I can calculate joules. I can calculate energy. So I have 3.668 watts for this amount of seconds is that many joules. And what I've done is I've used the capability in our product. I've also filtered. I filtered and set up another setup. So basically, the values on the top are not the input to the drive. They're just filtered. They're the full spectrum values of the drive output. And then the values at the bottom, I've now applied a filter to the fundamental only. The difference between the fundamental only calc and the full spectrum calc is heat loss. It's lost in the winding. So if you know the delta between those two, I can calculate for one full operating cycle 0.82 joules of heat loss in the winding, which is going to end up radiating out of the winding somehow, heating up the device, causing discomfort for the hand or reliability problems. So this was a very key measurement for the customer to make. Okay, now basically during the reversal cycle right here, I can now zoom in on that reversal cycle here. I can see the reversal happening, the current undergoing some very dramatic changes. I now only have one cycle, so I only have one level in all of my voltage, current, and power plots. You can see the sync signal displayed right here. So again, now I have this much power in the reversal. And it's all heat loss because you're going one direction, you stop it, you go the other. That's all lost as heat. So in one full cycle, I basically have 0.59 joules, going back one slide. During the cycle, 0.82 joules. If I sum those two things up and multiply by the number of cycles in a minute, that'll be my heat lost in a minute. So pretty cool capability. Now, they saw something else here that I alluded to earlier, and that was that in one of the rotational directions, they saw a vibration that was present in the motor, and they could see that in the per cycle power and apparent power waveforms. So again, these are now all my voltages and currents, and I've just overlaid them on top of one another. And here's a clockwise rotation, counterclockwise, clockwise, counterclockwise. This is the speed signal right here, is this orange signal, right? So that's the speed signal telling it to go clockwise, counterclockwise, clockwise, counterclockwise. And then this is the actual speed or reversal initiate signal that we showed earlier. Then these are my per cycle waveforms. I'm showing again the reversal, reversal right here, and these are the rotational directions. Here in this clockwise direction, the power is very steady. Here it oscillates a lot. So what they did is they looked, grabbing the encoder position off the rotor, which is a voltage feedback signal. They just wanted to look at all that data, and what they found is there was something in their control system that was causing this behavior. I cannot disclose what they found; it's proprietary. But they used this information to understand a behavior happening in the counterclockwise direction that caused this oscillation. And so, if I look at a very big value or a very big view of just that oscillation, you can see it very clearly here. There's near constant power delivery on a clockwise rotation, but there's a very oscillatory power delivery here. Now, if we covered up these waveforms of power versus time, if we covered them up and didn't look at those, and we only saw a mean power value, we would have had no idea there was anything wrong. So this is when we talk about the dynamic measurement capability and the ability to see dynamically how your system performs over time, tie it back to your control. It gives you the ability to debug. And they had a happy result. When they modified their control scheme, they were able to basically make the clockwise and the counterclockwise rotation operate nearly identically with the same kind of power behavior. So that was a very big win for them. All right, so just a quick solution summary again. The dynamic capability here is where this solution really excels. This customer wasn't trying to measure efficiency to 0.2% or power to 0.1% or anything like that. They really need to find big problems. They found it, so this was the best solution for them, and especially for the control and the power interaction and the control debug, which only a scope could do. And that's the core of our product is the platform of our product that at its core is an 8-channel 12-bit 1 gigahertz scope. All right, so we're just going to pause very briefly and ask the third and last polling question. I just ask you to choose one of these. Just let me know what your principal design and or test role is at your company. Maybe you're involved in magnetics or motor design. Maybe you work specifically to validate or understand operation of different IGBT and MOSFET devices. Maybe you start to design the inverter sections, the H-bridges and the cascaded H-bridge inverter subsections, or flyback transformer, something like that. Or perhaps you're an embedded control system engineer, either hardware or software, or maybe you're system level. You take everything and you integrate it into one cohesive whole. So just answer one of these questions for me, please, and as soon as we're done with the polling, we'll continue on. Okay, we'll just take a few more seconds for those who've started the poll to finish it up. Okay, now we're ready to continue. Let's look at another example. It's a vehicle propulsion motor, and this was done as an evaluation on a test stand. So we were lucky to have a dynamometer with some analog torque load cell, and an analog tachometer to measure the drive output, and the motor shaft mechanical output. So we also looked at harmonics and THD in this example. So this is probably starting to look pretty routine. Again, this customer liked to use the 2 wattmeter method. So here's my line-to-line voltage signals here, and here's my drive output signals. They did use 2 different types of current sensors. There's a lot of flexibility in what you can use to measure current. So they had 2 different things here, which is why these signals look so different. Then they sensed the torque load cell output with one of the channels on our input. That's this right here. This right here is a zoom of this thing above. So we vertically zoomed this signal. And we have 12-bit resolution in our oscilloscope. So as you zoom it, you can really get to see a lot of detail, which is pretty cool. I can directly see the motor torque ripple on that torque load cell, which is not so obvious right here. Then this is my tachometer output right here. It's an analog voltage signal. Then I've calculated speed per cycle based on the inputs. We've talked before how this can be done. So I've calculated speed on each power cycle, and I've calculated the efficiency also on each power cycle, and those are displayed right here. Also, I should point out I have the calculations for the drive output on this line, this top line, and for the mechanical motor shaft output, we calculate this much power based on the input of those torque and speed sensors, and from that, we get the efficiency of about 74%. Okay, in this case, the customer wanted to correlate efficiency to torque, which was pretty easy. So if I took that zoom waveform of this torque load cell up here, and I just moved it down here, and I just laid the efficiency plot, the calculated efficiencies plot right on top of that, I can see the efficiencies correlating extremely closely with torque. I can also see that, you know, if I were to put amplitude cursors on this speed plot right here, this is speed, is orange, the amplitude of that is changing by about ±1 RPM peak to peak. And if I look at my statistics here for speed, I can see that. I see my min is about 98.5 and my max is about 100.53, which is about ±1, and I even have a standard deviation number here too, which tells me it's about a half an RPM standard deviation, which all that correlates with what I can visually see, except I can also, from this plot, I observe the torque ripple directly, as I did earlier. I'm sorry, I can observe the torque ripple in the speed plot as I could earlier. Okay, so now basically what we're showing here is the same data set. I've zoomed and gated, so here are my zoom waveforms right here. These things also zoom at the same time. And what really I did here, what the customer did here, is to correlate the filtered analog waveform with the calculated waveform. This was just actually his check to make sure we were calculating speed correctly per cycle. And so we took his speed sensor, which is this right here. I vertically zoomed it. So I took this amplitude and I turned it into this amplitude with a vertical zoom. And then I just took a low pass filter of that and set that up as a math function, which is F11 in this case. And you can see the math function of the analog torque, analog tachometer signal really follows the same profile of the calculated speed. So this was his way of understanding whether we were making the calculations correctly, and of course we are. Another thing we can do is we have capability to measure the total harmonic distortion, and we can do that on a per cycle basis. So we can give you a mean value. So if I just turn on THD, I can display the mean value in my table. So it's about 7.5% voltage and 10.5% current on a mean value basis. But if I click in these cells, I get waveforms, which are shown here. So current THD is displayed here, and voltage THD is displayed here. And I can see the variation of those on a cycle-by-cycle basis. And I also see it in my statistics table right here. I've got 82 calculated total in my acquisition. And I can get all this capability. All I have to do is go to my harmonic filter in my setup, and I just choose fundamental plus N. I choose a range. It can be up to 50, and I can make all these plots the way it's done right here. Okay, so a quick solution summary in this application. Again, this solution really shines for the dynamic analysis. Also, on the mechanical side, we have a lot of capability to look at those speed and torque signals in a way that a scope-based platform can do, but a power analyzer cannot. And we showed THD measurement capability. You can get a number here. It's pretty limited. Here you can get numbers, waveforms. You can filter in a variety of ways. One thing that's worth noting and pointing out, this kind of selection here is all done post-process. So I can grab a waveform and I can have it on the screen like I see here, and I can change this selection as much as I want. It'll recalculate. It's not like in a power analyzer where all the calculations are made on the fly in an FPGA. And if you want to change those calculations, you're out of luck on a power analyzer. You have to take a new acquisition. With us, we take one acquisition, everything is post-processing. So it gives you a lot of capability to change things up and try new things out. Okay, let's talk about the harmonics calc a little bit more. I showed you these THD waveforms here. This is just a small drive output I use for example's sake. As I showed you, we can plot the THD over time for voltage, current, and voltage, power, and current. And I get these mean values right here in this table, and I get the variation of that over time right here. I can zoom and gate all those. So as I did not show before, and I'm showing now, if I use zoom and gate, now my values change. They change to just the area. So I can see here, this drive is under stress in this location. And I can see that on the current waveforms. I can see it on the voltage waveforms here as well. And I see it in my calculation. So if I go back one slide, my average for the full acquisition was 3% and 2% for voltage and current. And if I go here, it's 4% and almost 3% for current. So there's more harmonic content here. That may still be very acceptable, but there is a lot more, and I can plot that over time. Actually, these waveforms give me the ability in the full acquisition to see where I have a peak. So I can say I have a peak right there, and I can just zoom around that, and that's now rescaled and shown right there. We can also do a full harmonic spectral analysis. So I can turn a table on, and I can choose to show whatever I want, whatever spectral view I want to see, and that's shown right here. So we look at the voltage, the current, and the power spectrums right here. And I can have up to 9 of these on at any one time. I've only chosen to put 4. And then it gives me a table which shows harmonic orders and the frequency. This is a variable frequency drive, so it's going to show me the frequency, and then it shows me all the calculations. I've selected microwatts, microvolts, and microamps here. I can also show it in percent. I can put a limit test on it if I want to limit it to a certain value. Okay, so for harmonic filtering, we use a software technique, as I described before, which is very valuable. It's post-process. I can change it all I want, and it has a lot of flexibility to adapt to very dynamically changing events. Power analyzers have a hardware-based harmonic filter. It's a hardware PLL. It has a PLL loop bandwidth. It has a very limited ability to adapt from cycle to cycle. And so that is somewhat of a limitation for this kind of calculation. We also can do harmonic analysis dynamically. So we're not just giving a mean value, and it's done using the same tool set that I described earlier. And lastly, the THD measurement. We provide a measurement. Power analyzers do as well. We also can do that THD, though, dynamically, which is very helpful. Okay, let's talk about device analysis. A lot of times people use scopes for power analysis on their device. It's worth just covering this topic in a few minutes. And this may look very familiar. This is an IGBT example or a MOSFET example. I'm showing an IGBT here. But device engineers usually want to understand how efficient their devices are for switching and conduction loss, and they want to calculate an RDS on, if it's a MOSFET. Maybe look at DVDT, DIDT, and understand safe operating area. So they'll use typically a scope, 12 bits better than 8-bit resolution, and they'll use some of these other pieces of equipment as well. One that's very helpful is this differential amplifier, which has a very good common mode rejection ratio and excellent overdrive recovery. So it's great for measuring the conduction. But a lot of times people use a variety of other voltage and current probes that are supplied by oscilloscope manufacturers, and then some sort of software to make measurements. This is a specific example here showing an acquired drain to source voltage on a MOSFET. This shows the drain current right here. And then we're doing some automatic calculations. These color-coded overlays show on the turn-on, turn-off, conduction, and off-state zones. So here then we just provide parameter values in one of our packages that show what these values are. And it shows a mean value and also shows the number of measurements and the full min and max and other statistics around the measurement. If I really wanted to focus in on the conduction loss, what I want to do is I want to get that zone. I really want to overdrive my scope. The problem is most scope front ends are not capable of being overdriven in a good way. They'll fail very quickly. The days of the unbelievably great analog front ends on scopes, if they ever existed, are no longer with us. And so typically what people do is they'll use this differential amplifier, the DA1855, which really just has just an awesome analog front end, and it can really be pushed hard and overdriven, and it has other characteristics too that make it ideal for this measurement. So what we've done here is we've used that DA to overdrive into the scope, and it's limiting the voltage level in the scope so you don't get a lot of ringing or bad performance. And I can see right here now this particular conduction loss cycle. My software identifies that as the conduction zone. This is my drain current, and then I can calculate RDS on, or I could calculate power quantities as well, and it's usually done. You have the ability to take very long records of many cycles and calculate values, and also show what we call a safe operating area. So this is the voltage over time, or the power of the device, and I can show on this XY plot, I can show a mask, and then it'll indicate failures. And I can define the mask however I want. So it's a great way to show how my device might be operating in circuit under load. So in this example, really power analyzers can't do any of this. Scopes are typically done. A lot of people use 4-channel 8-bit scopes. They're okay. A 12-bit platform like our MDA, our motor drive analyzer, is better. Using that DA1855A differential amp is really ideal for the conduction loss measurement. Okay, quick summary, then we'll give you some resources, and then we'll take your questions. So we presented this earlier. Now you have a little more context around it. You have power analyzers. Good ones integrate both 3-phase and motor and give you complete motor mechanical power in doing so. Then you have scopes. And scopes are really on the complete opposite end of the spectrum. They're used for control debug. They work great, but they're a very limited tool. You get an 8-channel 12-bit scope. It can do a lot more for power, especially 3-phase. It can show you long waveforms, which is great. But the motor drive analyzer kind of brings it all together, gives you the power calculations, really gives you a lot of dynamic capabilities that you can't get any other way. And at its core, it's a 12-bit, 8-channel, 1 gigahertz oscilloscope platform. So it does all the things a scope does. And it has super long memory and great serial trigger, decode, mixed signal capability as well. You can visit us at this site. It's teledynelecroy.com/static-dynamic-complete. We've got consolidated all the information here on this site. You can watch some videos, get some application notes. You can request a power poster at this site that looks like this that you can hang on your wall, which gives a nice summary of line voltage, current, and power. That's been a very popular poster, so you might want to check that out. We'll also be at APEC in a few weeks in Long Beach, California in the USA, and I'll actually be there. I'll be doing a discussion of this efficiency calculation in dynamic operating conditions, and that will be at this location right here. So if you wish to come by and visit us, please do. Please come see my presentation or stop by our booth. We're at booth 2037. Love to talk to you. We'll have myself and several other people there. Really the most power electronics knowledgeable people in the company will be there. We'd love to hear from you. So at this point, we'll pause for any questions, and Guido is the person that on the other end of the line here has the question, so I'm going to ask him to take over from here.
So Ken, right now we are waiting. Okay, we have the first one coming in.
Okay.
It's about sending the slides, but of course we will. Maybe you can just drop us a quick email about that. That would be very helpful. And I'll send it to you later. It's a very common request. Any other questions? So now, Ken, so what are your views on MDO and mixed signal scopes for?
Guido, your voice is fading out.
Oh, sorry, I'm moving my head a little bit. Sorry.
That's good.
What is your view about the MDO and mixed signal scopes for power measurements?
Right. Okay. So when you say MDO, I'm assuming you're referring to a product from a competitor called they call it a mixed domain oscilloscope. And so if I just go all the way back to one of my slides here that shows, you know, like a solution summary for a 4-channel 8-bit scope, those are still 4-channel scopes. They're still 8 bits. There's a lot of scopes that kind of generically have the message about them as 5-in-1, 6-in-1, 7-in-1. Sometimes they combine an RF input with you know, some sort of very basic ARB or some generator or something like that. Those really still have very limited capability in any kind of power application. They're nice bench scopes for basic needs, but once you get into a complicated application like power electronics or 3-phase power measurements where you want to measure power quantities and understand dynamic performance and how things are working with your control system, that product is really not going to be any different from the user's perspective than just a basic 4-channel 8-bit scope.
Okay, another question, Ken.
Sure.
The question is if our equipment can provide CAN bus analysis to measure the speed setting time from commands received.
Yeah, that's a great. I think I know what the question is. I think the question is when you integrate into your product the speed, can we take a CAN signal that contains speed information and extract the speed from that and use it in our package? And the answer is not today, but we do have that native capability in a product we call CAN bus TDM, which can do that. And you can do that using a symbolic file. And we do have interest in integrating that capability directly into our motor drive analyzer. So that the core capability exists, we just have to link it to the speed calculation in our motor drive analyzer. And that's something I always hesitate to make promises, but that's something I kind of envision happening sometime during this year. Perhaps the person asking that question is somebody that was one of our beta testers. It comes up very commonly in an automotive application, a vehicle propulsion application. So it's a really good question. We've heard that request a lot, and I think it'd be a great thing to do.
So there are no other questions there right now. So if you have any, please write them now.
Okay, good. Well, my contact info, I believe it was at the very beginning. I'm going to go all the way back to the beginning. My contact info is on that first slide. I think you'll get a link to the video, and you'll be able to reach me. My email address is ken.johnson@teledynelecroy.com, right here. And always happy to hear from people. Email is the best way to reach me. I do travel sometimes, so you might have a 24 or 48-hour wait, but I do like hearing from people, so feel free to contact me directly as well. And I thank you for your time. And Guido, if we don't have anything further to cover,
there are no other questions.
Okay, well that will conclude our webinar. I thank you again for attending, and we look forward to talking to you in the future.